Okay, earth science time. Yeah, that's the correct response. Today we're talking about minerals. Something I'm interested in is to hear about your bell work, which was something like, as an exploration one.
It says,
interpreting graphs of composition. It says, please read it for us, Kyla, as you were about to before I interrupted you.
Can I just do the analyze box?
Sure.
It says, look at the graph of common elements of Earth's crust. What are some familiar elements that are not shown in the table? Is it surprising to you that they are not shown? Why or why not?
So first let's list the, in order, the most common. Let's do the top 5 most common. In fact, we're going to do 4 most common and then kind of 5 through 6. But anyway, what's the most common element in Earth's crust?
Oxygen.
Now, the question was, is it surprising that any of the elements are not listed? But is it surprising to you that oxygen is the #1 element in Earth's crust? No, you're not surprised by that because you're smart. But why might it be surprising to an idiot?
Because they would think oxygen is in the air.
Yeah, oxygen is in the air.
Not
only idiots think that oxygen is in the air, real people think that too. There's no such thing as idiots. It's surprising because oxygen, as you say, is a gas. They might think it's only in the air, so they might not realize that oxygen is the #1 element by mass in Earth's crust. What is the #2 element by mass in Earth's crust?
Si.
Which is?
Silicon.
Silicon. And what's the percent of silicon in the crust?
27.7%.
27.7%. These two things together make a polyatomic ion called SiO4 2-, which is called the silicate, or silicate is how we usually pronounce it, ion. This, I was about to say the majority, this makes up a whole category of minerals. We're talking about minerals. We group minerals into 2 categories. Of all the minerals, which we'll talk about the criteria today, but we're also going to talk about the categories. And first let's talk about the categories. One broad category is the silicates. The other broad category is the non-silicates. That's how important silicates are, is that we just group minerals whether they are or are not silicates. What do you think this category of minerals has to do with this polyatomic ion?
Can you repeat that?
What do you think this category of minerals, the silicates, has to do with this polyatomic ion, the silicate ion? They have the same name, but why do you think?
Because it's made up.
Yeah. Because this category of minerals all have this polyatomic ion in them. It's as simple as that. The silicates. Let's keep our list going. We're going to come back to this. Well, let's keep our list going. I'm going to move the word criterion over to the other side of minerals. I've kind of gotten a little bit disorganized. Criteria. And we're going to talk about that later. We will, I promise, if there's enough time. If there's enough time. What are the other elements in Earth's crust in order as we go down the list?
And then we get into aluminum.
Aluminium? Yeah, it depends. The actual IUPAC pronunciation is aluminium, although they do accept aluminum. But Professor Dr. Sir Martin Polyakov, I said those all wrong, or Sir Dr. Professor Martin Polyakov from our periodic table of videos says that it's important to spell it this way, and it really is, because in the same way that we want to have units that can be communicated worldwide, which is why we use the SI, like meters, seconds, etc. If we're searching on a database for articles that are about aluminum, and we spell it the American way, we're kind of robbing ourselves of, I would say, somewhere between 1 and 3/4% of the 1/4 and 3/4 of the articles that are out there, because they might be spelled aluminium. And so really, if we have a useful search engine, we can just put aluminum or aluminium, or even if it's a very smart search engine like Google is, you could put this in and it would come up with also aluminum, or you could put aluminum and it would also come up with this. But anyway, this is the accepted spelling.
I like how it's spelled.
It also
sounds better.
It also matches the other elements, like gallium, einsteinium, fluorovium, all those things in an EM. Anyway, aluminium makes up what percentage of Earth's crust?
8.1%.
8.1%. Are you interested that this is that high on the list? I kind of am. I still am.
Yeah. I didn't really expect that.
This is the most abundant what in Earth's crust? What kind of thing is that? Metal. Yeah, it's the most abundant metal. Silicon's a metalloid. Oxygen's a non-metal. Doesn't it seem kind of interesting to you that we think of Earth as being made of solid stuff? It is made of solid stuff. But we think of Earth's crust as solid, and we're looking at the periodic table, we'd be tempted to say that of course it would be made of stuff that's mostly metals, because those are the solids. It's not all the solids, and there certainly are solids that are not metals, and there are metals that are not solids, but we would think that the Earth's crust would be largely metallic, but only 8.1% of Earth's crust is metallic. I think that's kind of interesting. And obviously, it's not like your pie chart. The Earth's crust doesn't look like that. It's not like one whole corner of it is oxygen, and then another corner is silicon. These are all mixed together, or rather, they're chemically bonded together. What's the next one?
Iron.
Iron, which is another metal, and it makes 5.0%. And then the rest of them, not the rest, but many of the others the rest I want to group together. Calcium, sodium, potassium, and magnesium. Calcium, sodium, potassium, and magnesium. Where are these all located on the periodic table of the elements? They're all what, first of all?
They're all, not metals, but
They are all metals. They're all metals, and in fact they're all reactive metals. They're all in groups 1 or 2, meaning they all have 1 or 2 valence electrons. They're reactive. In fact, they usually react with oxygen or the halogens. So what are some things...
But
now we get to the next question. Go ahead.
What I thought was... Were you asking
Yes,
questions?
now
Okay,
I wish I had
because
my tea, though.
that's what I was going to say, is I think it's weird when you think of like sodium and potassium. I don't think of those to make up like the crust. I think of like mercury or like magnesium.
The heavy metals, maybe.
Yeah.
Yeah. And really, people a lot of times don't even think of sodium and potassium as metals at all. I mean, like a lot of times, because people, when they're freshmen, are not really interested in anything that is not related to their hormones and body odor and hair and everything like that, they're not usually interested in this. But in physical science, if they would actually pay attention, I think people would be interested to find at that age that sodium and potassium are metals at all. Because we think of them from the time that we're young, or at least I did, in terms of biology. Like you got to have sodium in your diet, or you have too much sodium in your diet, or my grandma had a heart attack because she didn't have enough potassium, or whatever. But they are metals, and your body uses them as metals. Even if we look at them, if we had a lump of sodium, we could wad it up like Play-Doh. It'd be even easier with potassium. They don't act like what we think of as metal. Iron obviously does. Aluminum is what I was just knocking on. Magnesium, your phone case is probably made out of magnesium. It might be, if you have an iPhone, you probably both do, you're rich. It's probably aluminum. But many phone cases are made out of magnesium. Anyway, all these things are the actual metals that make up Earth's crust. Now, the other thing I want to point out is this is all talking about what part of Earth? We said it many times. This is the crust, which we might, this is different for the lithosphere, but we call this outer layer, just as a review, this would be the crust. We call this area here, altogether, we call the what?
Lithosphere.
Sure. This is going to be not very good to scale. I want to call this the crust.
That's the crust.
I want to call this the lithosphere. I want to call this the mantle. And I want to call this the asthenosphere. Sorry, that should all be one word, but I ran out of room. And then I want to call this the outer core and this the inner core. Outer and this the inner core. Anyway, all that we just talked about is just the crust. It's hard to tell. I had a real problem with this. There was a TikTok last year that I watched about this girl, I would assume a freshman in college, but she had just been to a college class, and she was saying it was mind-blowing to her that no one knows what the core is made out of, that people assume what the core is made out of because of these kind of studies. But what she was ignoring or forgetting or not knowing yet in her college career is that almost everything in science, except for like how many fingers are on your hand or what trees look like, almost everything in science we actually know from indirect measurement. So we do know, as much as we know anything, we know that the core is made of iron and nickel. So if we were doing this list for the whole Earth, the ratios would be way different. But this is the crust. And why is it important? Even though the crust is this tiny, tiny little bit, it's actually, interestingly, it's almost the exact same ratio as if you had an apple. The skin of the apple compared to the whole apple is about the same ratio as the crust of Earth compared to the whole Earth. But why are we worried so much about this? Why are we worried so much about the crust?
Because that's like what we live on.
Exactly. Just like that girl said, we have no direct experience with what's in the core, inner or outer. We have no direct experience with the asthenosphere, and we have exceedingly little experience with the lithospheric mantle. Almost none at all with the mantle. The crust is, even though it's a small part of Earth, one, it's all we've got to go off of, and two, we can, if we use indirect measurements, we can, and we use our noggin a little bit, we can learn about everything here just by examining the crust, just this. It'll tell us, if we look in the right places, it'll tell us everything we want to know about the rest of it if we investigate it correctly. And this whole class is about investigating it correctly. Questions about that before we move on? Something that we must know about minerals is this criteria. I'm going to pause this and I'm going to run back to make sure I can actually see what I'm pointing at on the video. Oh, and I'm going to switch it to picture-in-picture mode. Oh. Okay, things look pretty good back there. So here are the criteria. By the way, each one of these things, the singular of the word criteria, you've heard the word criteria, things on which another thing depends. The singular of this is criterion. This is how a lot of Greek words end in on, and we pluralize them with But anyway, here are the criteria for it to be considered a mineral. What must a mineral be? You read your exploration, you should know these, but what must a mineral be?
A substance that has...
Okay, so let's focus.
It has to be a substance.
Okay, substance. Which we know from chemistry. I mean, we might just read that and think it's a fancy science way of saying thing, but ketchup is not a substance. Ketchup is a mixture. We remember from chemistry, which you're both in, that a substance has to be pure. It has to have the same composition.
Yeah.
We'll put a determinate. What's the word determinate probably mean?
That, like deciding.
Yeah, it's the same every time. It's been decided, basically. A determinate composition. It has a set composition. Sometimes, especially in minerals, that can be kind of vague. You sometimes see things like Barrel's formula might be Be sub x, Al sub x, O5, SiO5, maybe. And what that means is they kind of have a variable amount of those within a certain group, but each one of those barrels fits that formula, and they would all have their own specific formula we could determine. Anyway, what else must it be? Go on with your definition. I'm sorry I interrupted you. Substance that, what was the next bit? I'm going to interrupt you again.
Has a very specific characteristic.
Okay, so it meets certain specific characteristics, and that's what these criteria are. What are the rest of the characteristics? You said, or maybe you have it. What are the other characteristics this must have? Try to think of it without having to, oh, I forgot my dang tea. Try to think of it without having to look if you can.
It has like,
What are properties? Just think about a mineral. What else must it be? Yeah, that's the determinate composition, and it has to have a set chemical formula. What must a mineral be? Can you think without even looking?
Can it be like a compound almost because it can be made of?
We said that already. Substance, a determinate composition.
Pure.
It is pure. It's a pure compound. What you're thinking is it might not be a pure element, even though some pure elements are. That's why we use substance instead of compound. This means either element or compound, but it must be what?
Well,
Think about a mineral.
In other words, it is in the form of crystals.
Okay, so it has to be crystalline. And what's that mean? You remember from physical science? It has a crystal lattice. Maybe that helps.
No.
This is the way we define a lot of minerals, actually, is by their crystal lattice. And the crystal lattice is spelled like that. But it's a repeating pattern. You know the word lattice. You might have lattice work underneath your deck. A lot of people do. A chain link fence is lattice. There's lattice work in sewing. And this just means it has a repeating pattern. In the case of crystals, what is repeating here? Is it chain links? Is it wood struts in a deck lattice? Is it
No,
sewing?
what I think of is like when it's like when we did our crystallization, it was like the salt forming on top of salt, which formed on top of
And
salt.
what is forming the actual piling there? So even though we can see the crystal on the big scale and it looks like this is what we see. But if we zoom in, even the what is made to shape like that. The what's?
The particles.
Yeah, the particles, which we call what are the particles?
Atom?
Atoms. Yeah, even the atoms are shaped like that. So it's actually the microstructure, the microlattice determines the macrolattice. You know the phrases micro and macro. Micro meaning too small to be seen, macro meaning large enough to be seen. Anyway, it has to have a crystalline lattice. It must have a repeating pattern of atoms. And that's not true for everything. This is special. Not everything does this. Glass is an example. It isn't a mineral. It meets the other criteria, but it's not a mineral because it doesn't have a repeating pattern. Obsidian. You know about obsidian? Sean, she says wistfully. Obsidian is not a mineral because it is not crystalline. It doesn't have a repeating pattern of atoms. We're going to talk more about obsidian later. What else must a mineral be? I'm going to erase this bottom bit if you're done with it because I want to have them do my categories again. Is that good? You can always rewatch the video too. I'm also talking pretty fast on this because I want to get through it kind of fast, and also because I know you're both good students, and if you want to see this again, you can always watch it on.
They have to occur naturally.
Okay, naturally occurring. So even if we have a lab-grown diamond, which is chemically identical, has the same crystal structure and same determinate composition as a real diamond, it's still technically not a mineral because it was grown in like the human beings made it. That becomes real difficult actually because there would be no way, if humanity all died tomorrow in a million years, an alien life form came to planet Earth and had these two diamonds, there would be no physical way for them to tell them apart. So this one's kind of fudgy. I mean, it's true, but you have to have some history of that diamond to know it wasn't naturally occurring.
It sounds like it's contradicting itself because it says that it has to be a naturally occurring, but it has to form through inorganic processes.
Yep, and that's the next one. Inorganic. Which means not only is it naturally occurring, but some parts of nature don't count. No what? What can't be making it if it's inorganic? Not just no humans, which would make it synthetic instead of naturally occurring, but no what can make it. Not made by, I was going to put no this thing, but I'm going to change it to not made by what? What would it be if it was organic?
It'd have to be like made by the earth or whatever. Mm-hmm. You know what I'm trying to say?
No, but yeah, you're thinking almost all this stuff is made by earth. But specifically organic means it's made by life. So this, oh, where'd it go? I must have dropped it. Mm-hmm. Oh, here it is. I moved it. I didn't drop it. This gave me this. This is a substance. It has a determinate composition. It's calcium carbonate. It's not entirely, especially not the purple marker on it. But it is calcium carbonate. Determinate. It's crystalline. It did occur naturally. I didn't make this. Biz didn't make it. She wrote on it. But it is not inorganic. It was made by a living thing. So really, we could consider this kind of a subset of this, but we do still list both. And then the fifth is it must also be, well, you're missing the simplest, easiest one. What must minerals be?
Solid.
Yeah, they must be solid. Specifically solid at room temperature. And this one, so there's a confusion about ice. This is true, but some people somehow overlook this and say that ice is a mineral, but it's a liquid at room temperature. So in my opinion, from what I've known about minerals, ice should not be considered a mineral. I even watched a TikTok of a guy I esteem highly, Hank Green, at Hank Green. I could really be calling these people out in my YouTube description. But Hank Green has a TikTok where he talks about how you are a lava monster because you're 70% water, and water is molten ice, and ice is a mineral, so you're technically magma, and you're made out of that. But minerals must be solid. At least, your book even mentions that ice is a mineral. But then it just, right after that, says it must be a solid at room temperature. So there is some confusion about ice. If you list ice as an example of a mineral, I'm going to probably write a little note to you, but I don't think it's wrong, or at least apparently not everyone, including Master of Science.
Glacial ice.
Right, I know. So your book thinks it's right. I'm fine with it. Whatever. I do think it's interesting that you could be technically a lava monster, according to Master of Science Hank Green. He does have a master's degree in science, so that's fine. But I've always heard that it has to be a solid at room temperature, which would preclude ice. Anyway, most minerals we could could say have to be that. Although I don't like that, the fudginess of that. Minerals must fit into all these criteria. Every mineral must be made of that. Let's talk about, your book doesn't even go into the types of minerals until the next unit. Oh, no, it doesn't do it at all. That's a rocks. Well, I want to talk to you about the categories of minerals real briefly because I think it's important. And then we're going to talk about properties of minerals right after that. What time is this class over?
10 minutes.
Wait, we should be able to get through there. So within the silicates and the non-silicates, there are some groups of silicates. I know there are things like chain silicates, sheet silicates, which are further broken up into phyllo and leaf silicates. But let's just give some examples. Some common examples of silicates, and these are not groups, these are just examples. So I'm just going to put an example there. Quartz, you've seen quartz, which includes things like amethyst. You know about amethyst.
I have an amethyst.
Amethyst is beautiful. Amethyst is quartz. Rose quartz is quartz. There's something called smoky quartz, clear quartz. Quartz is a very common silicate. If you've been to a beach, the sand is probably the mineral quartz, most likely. Another very common one is feldspar. It's not always pink, but a fairly easy way to tell feldspar is that a lot of times what we call orthoclase feldspar is pink. If you see, like the granite we saw at Harney Peak, the little pink streaks in that were orthoclase feldspar. There are other kinds of feldspar. In fact, this one here, I'm sure you can see it on the camera, this one here is a piece of granite, but the pink within it, that it largely is feldspar. So it's both granite, the rock is granite, and the mineral is made out of is
Look at this
feldspar.
website. Feldspar versus quartz. What's the
There you go.
difference?
There you go.
There's 5 crucial signs.
You read that later. Another silicate that we come in contact with, another mineral silicate that we would rather not come into contact with very often is asbestos. This is not a very common example, but it's one that we know about already, so let's put it up there. Asbestos is a silicate. And there are others. I'm just going to put et cetera for this last one to save some time. There are, actually, I think there's something like 2,000 other silicates, so there are a lot. I think there's something like 4,000 minerals altogether, and roughly half of them are silicates. Prove me wrong. I really might be wrong, so do prove me wrong. The non-silicates are a broader group, and these include native elements, where it's just the element by itself, like gold, copper, silver. When those things show up in nature just all by themselves, which doesn't happen anymore. Hey, what's one reason? Can you guess why we don't just trip over chunks of gold no more?
Because they all been mined.
So, yeah, right. Because people have liked gold for a long time. There used to be native element deposits of gold in the Middle East, especially. In fact, if you ever read the Bible and you read about how they got a lot of gold, they don't talk about how they got it, but they talk about that they do have it. They talk about like, oh, it's 40,000 talents of gold or something. Most of that would have just been like some dude walking along, he's like, oh, shiny, and he picks it up. Like the gold would have just been on the ground, and then because people like gold, they just kept it until there's no more gold on the ground, which is kind of interesting. Native elements, we have halides, which involve halogens, so some metal bonded with a halogen, metal fluoride, metal chloride, etc. Sulfides, oxides, sulfates, I'm trying to think of some others. Carbonates are a big category actually. Limestone. This is not a mineral, but it is made out of calcium carbonate, which would be a non-silicate mineral if it was one. Limestone is made out of the mineral calcite, which is very common. Okay, and lastly, and we'll talk more about these in your lab, but I just wanted to define the basic properties by which we identify minerals. We usually spend, in fact, in the previous years, there was a whole chapter about the properties of minerals. And before we changed the book, I'm going to rewrite this so it's spelled correctly. There was a whole chapter in the book about I did it again. About the properties. Just ignore this. It's supposed to say the word properties. Look, you can spell check it. But this book apparently doesn't want to talk about it very much. What's the most obvious property of a mineral? It's not very useful, but it's very obvious. If I had a mineral here, you would be able, even if you were in kindergarten, to tell me it's what?
Check.
Sure. We'll do that one next. Luster is shininess. But think about if you're a room of kindergartners and I bring out some random mineral, which I wish I had, should have thought ahead, and I hold it up, I would say, how would you describe this mineral? And 90% of the kindergartners would say it is. No, they wouldn't, because it might not be.
It is
a rock.
hard. A rock.
They would say it is purple or black or orange or color. This is the least useful. God, I spelled color before I changed it. I'm going to have to cut this because what's wrong with me? Let's pretend I'm British and not stupid. Color. Oh, golly. I give up. Anyway, color is not useful for two reasons. One, if I had a certain kind of mineral, which meets these criteria, if I had any given mineral, that mineral could come in 30 or 300 or 3 different colors. So I could have blue beryl or green beryl or pink beryl or red beryl or any different color in between. Not only that, I could have black beryl and I could also have black hematite. And so almost every mineral can be black. And so color is useless because any mineral can be black and one mineral could be 17 different colors. So we almost never use color. It's very, very rarely a good idea. Like I said, feldspar, a lot of times just recognize as pink, but not all feldspar is pink, and not every pink mineral is feldspar. What's another property minerals besides color and luster? Well, we've got something called density, which can be very handy for some. This is the one, I like this one because we can use numbers to measure it. We can't really use numbers to measure color. We could, and we sometimes do. We don't really use it for luster.
Density could be useful in like the difference between like real gold and like fool's
yes,
gold.
Yes, exactly. Mm-hmm. That's one classic example. Density is, we use numbers, so I kind of like that one. But also minerals can have a wide range, not a very wide, but a somewhat wide range of densities too. Color, luster, density. Hardness, this one I like too because it has numbers. It's kind of a loose scale. But the hardness of a mineral we use by trying to scratch other minerals with it. There's a Mohs scale of mineral hardness, which you can see. Your book does talk about this a little bit, but not as much as I'd like. There's a Mohs scale of mineral hardness on page 68 in your book, which you should look at later. It's an exploration too. Color, luster, density, hardness, streak, which this is the color, but what happens is we scratch the mineral on a special plate called a streak plate, and instead of looking at the color of the mineral, it powders the mineral. Like it's basically sandpaper. No, not really, but it's kind of like sandpaper, and it draws a line of powder from that mineral, and that does usually have a specific color for a mineral. So feldspar has a white streak. So we get a pink or green or black feldspar, and then when we streak it, it'll be white. And so that's more useful because it eliminates the second problem, which is that this mineral can have 17 different colors, because minerals almost always have the same color streak.
It's like when I always remember at like recess. We would take rocks and like
you wasn't
chocolate.
I know. You had a good. You were doing streak, and you might have even found you had this pink rock, which was probably feldspar.
Yeah.
You streak it, it's white, and you didn't think anything of it. You might have been like, well, and you threw the rock at a car or something. But then there's also some special properties. Special properties like magnetism. These are very, very specific. Like if you find a rock that's magnetic, probably magnetite. There's a couple other choices, but it's probably magnetite. Effervescence, which I'm trusting you to look up all these words, and I spelled one wrong. Effervescence, fluorescence. There's lots of other. There's a cool one, my birthstone. Depending on how in-depth in the birthstones you get, my birthstone, I'm born in June, either pearl, I don't like that because it's not a mineral, but it was made by a living thing, or Alexandra, which has this cool property that under different kinds of light, it has different colors. So in firelight it looks orange, I made that up, it might be some other color. In fluorescent light it's green, in incandescent light it's yellow, but it changes colors depending on the kind of light, which is pretty cool. But there are others, etc. This is a very brief rundown of everything about minerals. This is super surface level. Every one of these, I mean, you could write a doctoral thesis about the color of minerals. Like, you can get very in-depth in this, but this is all of it at once. Do you have questions so far? Okay, we're going to have to call that quiz for the day. We'll do a lab that'll demonstrate these more, and it'll kind of help you understand these a little bit better. And then these categories, apparently your book doesn't care about very much at all, so we're not going to worry too much about it. Questions?